Okay, so let's start. So today we're gonna. So last time we were talking about this determination of the spectrum and in conformal gauge. Today we'll talk about an alternative way, well, a related way, via what is called BRST formalism. So Faddeev, Popov ghosts. And BRST formalism. Well, it's maybe more elegant way of describing the spectrum, and besides it has an interesting it's an interesting system in its own right, called BC or beta gamma system. So it's a ubiquitous system of conformal field theory. So that's another reason why we discuss it. Strictly speaking, we will not really need this formalism to compute amplitudes in the next lectures, but like say this topic is of its own interest, and well, if you want to study the string theory in full generality, so say in higher loops and so on, then this is really becomes important. But it's kind of a nice framework where some of the facts are more natural, look more natural, let's say. So, but we'll start with a so to explain the Faddeev-Popov description and so on, how ghosts arise from first principles is a bit would take us a bit too long. So we'll just look at some examples. So in particular, I kind of assume you studied it in electrodynamics, or if not, we will just start with finite dimensional integrals. So there is also some counterpart for finite dimensional integrals. Then we'll remember how it works in electrodynamics, and then we'll extrapolate to the string sigma model. So the first example will be just finite dimensional integral. So it's a bit far from what we're doing. So don't be too shocked with this kind of that we switch to this finite dimensional setting. But I think some main ideas maybe will be clear from that. The idea is that we want to perform some integral over some. So let's first try this. Finite dimensional example. So integral over some manifold M. So some manifold, and we have a group action, a group acting in this manifold, and we want basically to integrate G invariant functions over this manifold or over the quotient. So we will assume that G is a free action. This means that every orbit is actually G, a copy of G. So there's no stabilizer of any point, and so on. So of course, this is a very special situation. Not all actions are free actions, right? For example, the rotation of sphere around an axis is not free action because it has fixed points, for example, right? But this can be generalized to various other settings. Just this is easiest one to discuss. And moreover, we will assume that M2. So in the case of free action, the quotient is a smooth manifold. So, and we will assume that the map from projection of M to M quotient G is a trivial bundle. Trivial fiber bundle, so it's some fiber bundle with fiber G. We assume this is trivial again for simplicity. That is to say that M is a product of M over G times G. Again, so this can be generalized to various other setups, but but ultimately these topological matters are not that important because we will be considering integrals over this manifold. And for an integral, for example, if you erase some submanifold of measure 0, it will not affect the integral, but it will affect the topology of your. So basically, in most cases, you can assume it's topologically trivial. So, so the picture is as follows. Yeah, okay. So this is there is this isomorphism, but it is not a canonical isomorphism. So to actually properly define it, one needs a map called a section, which is map in the opposite direction, so from M over G to M. So this is a section. Section as in the sense of fiber bundle, yes. So if this is a projection, M to M over G, then the section is the map in the opposite direction that's compatible with projection. So in the points in gauge theory, so when we have in gauge theory, M will be some infinite dimensional manifold and G will be the gauge group. So G will be the infinite dimensional group. But we start with a finite dimensional setting where we just have this description. So there is this is pi projection, this is S section, and pi times S is identity transformation. So the picture is as follows. We have our manifold M, and we have these G orbits. So the action of G like this, and then the section is something like this. So the image of S. Yeah, so then the map from M times G to M over G times G to M is defined by the following. So you take Y G and you map this to G acting on S of Y. So this is this isomorphism that we have here. Y is a point in M over G, so you take its image. So you take the point, say here, this is S of Y, and then you act on it with a group element, so you come to some arbitrary point. So this will be the action of your by the group element. Right, so this is a one-to-one map. So there is a coordinate y on the quotient, which we send to the embedded submanifold S of M over G. And then we act with the group moving along the fiber. Yeah, so the choice of this section is like the choice of representative in each gauge orbit, right? So these are the gauge orbits. So in each gauge orbit, we choose some representative, some point, and altogether this becomes a submanifold, right? Instead of this, we could choose something else like that, maybe. That would be another section. So this is S prime, M over G. And so in gauge theory, these are the gauge fixing conditions, right? The choices of representatives in each gauge orbit. So this is a choice of gauge fixing.
Can I ask a question?
Mm-hmm.
Like maybe in the case of an elliptic curve, would a section be like you take all points out of like every parallelogram and like it's like a lattice? Like, well, I guess the question is, a section is like you take one point and then you map it to an infinitely many points of your.
I'm not sure. I mean, what do you mean elliptic curve? But what is the fibration? I mean, you have to have some fibration, right?
I guess.
No, I mean a section is a notion related to fiber bundles. So you have projection, and then you have a map in the opposite direction. So you lift from the base to the fiber, such that you map every point to the base, to one point in the fiber over that base, over that point in the base. So I mean, it's not just a abstract notion. I mean, you have to have some fiber bundle. So you have to have some projection first, then you have a section. It's kind of inverse to projection, right? In some sense. And generally, a general topological non-trivial fiber bundle doesn't have to have a continuous section or something like that. But here we assume it, so everything is topologically trivial. So, So, but it's okay. Don't bother with it too much. I mean, we will see what it means in practice. We don't need too much abstract notion. So. Okay, so now the question is that we want to integrate invariant functions over the manifold, and we want to reduce the so f is G invariant function. And we want to reduce the integral of f over the manifold to basically to the integral over the quotient. So so we want to reduce the integral over our manifold to the integral over the quotient. In particular, the quotient will be identified with its embedding in the manifold. So we want to pass from integrating over the whole manifold to integrating over this surface. And this may be useful in various cases. So for example, this is useful when your group is non-compact or has infinite volume, right? Then the original integral does not exist, but the integral over the quotient might exist. And this is actually the case of gauge theories or infinite dimensional groups and so on. So that's why it's especially useful in that case. So this volume form, quotient volume form means some volume form on the quotient, or the volume form on this section. So in principle, let us actually simplify the situation and consider the case when G is just U1. So one-dimensional group. Everything is generalizable to other groups. So in that case, well, actually, the quotient form, the volume form on the quotient is easy to write. So this is just a contraction of the original volume form with respect to the vector field along the action of the group. So V is the vector field generating U1 action. Okay. Yeah, and we want to prove, so the important thing that we want to prove is that the integral that we will obtain is independent of the choice of section, right? So there are many sections, like I said, but the integral should be independent of the choice of section.
Sorry, excuse me, can you repeat what means E with index V?
It's I with index V. Yes, it's just contraction with vector field V. So this is a form. You can evaluate it on some vector, right? So for example, if it has some, IV with any form omega p, by definition omega I1 IP minus 1 I vi dx I1 dx IP minus 1. Okay. Just contraction, so it becomes a form of smaller degree, right? So, for example, in that picture that I was showing, it precisely matches this case. So G is one-dimensional, so the volume form on the quotient has to be a form of smaller dimension, smaller degree, namely degree 1 smaller, right? So we take the volume form, and at any point we evaluate it on a vector along the action of G, so on this vector V. And it becomes a form well defined on the quotient, right? So if this is a point P, so this is a form well defined on the quotient T tangent space. Quotient quotient tangent space to the orbit, right? Orbit is here. This is a vector space along the orbit, vector field along the orbit, and the form so defined is a form on that quotient. Right? Because if two vectors differ by a vector field along the orbit, this will be 0 once you substitute here by skew symmetry of the differential form. So I'm just saying that this is a well-defined form on the quotient space. Okay, so we want to. So we want to. First, we want to show that the integral of f with this volume form over two different sections give the same result. So that means we have this manifold M. And actually, it doesn't even have to be sections. It can be just arbitrary curves or arbitrary hypersurfaces. This is L1, this is L2. And we want to compute the integral of f over L1 minus the integral of f L2. So by Stokes' theorem, this is the integral of f of derivative of over D12, where D12 is this thing here. All right.
Boundary or
what?
This manifold has boundary or just two L1 and L1?
No. These are some hypersurfaces in M.
But we have taken quotient.
Hmm?
But we have taken quotient.
Have taken the quotient? No, I mean we have just constructed a form of dimension one less, of degree one less than the top form, by contracting the volume form with the vector field. Now we want to integrate this over these hypersurfaces and prove that the integral does not depend on the choice of hypersurface. These hypersurfaces are meant to represent the quotient of m over g. Okay.
But m by g is finite dimensional.
Yeah. Now, so far everything is finite dimensional. Moreover, g is u1. So, right. So if g is higher, higher dimension, then you have to contract with all the vector fields generating its action. Okay. So you will get a dimension even smaller. So this will not be hypersurfaces. This will be some high codimension hypersurface. But it doesn't matter. Just imagine it's just a hypersurface for simplicity. So this is by Stokes' theorem. And now, well, we assume that the volume form. So everything is G invariant. So the original volume form was G invariant, U1 invariant in this case. Okay. So that means that the Lie derivative of the volume form was 0 along V, and that means that so this is d of quotient is 0. So the Lie derivative is d contraction vector field plus this. Just general expression for Lie derivative. So dx on volume form gives 0 by dimension. So one is left with this, and this is precisely the derivative of this new form, and that has to be 0, because this is an invariant form. So this is u1 invariant.
Can I ask another silly question? When we go from integrating over the manifold to integrating over the quotient,
Yeah.
why are we integrating over the section m over g and not just over m over g?
Well, that's technically one way of integrating over m over g, right?
The only way I can understand this is by elliptic curves.
Mm-hmm.
And so if we have C, our manifold, and then C over lambda is our quotient,
Yeah.
then we're kind of integrating over the complex plane and going to integrating over the fundamental parallelogram.
Yeah.
This section is like the Weierstrass P function. It takes the parallelogram to C, and so we kind of again integrate over C in the second integral, I think.
Well, I guess the example with elliptic curve is a bit too complicated for this, but well, that's technically one way of integrating over the quotient. The quotient is just embedded in your manifold, right? So that's one way of representing the quotient. Because I mean, in gauge theory, the point is that it's maybe the quotient is difficult to describe, but the submanifold is easy to describe because the submanifold is just your gauge choice. So we write some gauge condition. That's what we do in gauge theory, right? So for example, Lorentz gauge or something. That's the function, the vanishing locus of some function, basically. So that's what you're usually have in some physical setup. So we want to know, how do we integrate over that zero locus of some function? What's the correct measure on that zero locus of some function? And the correct means it should be independent of the function. The end result should be independent of the function because this gauge independence, basically. So yeah. But I think it will be more clear once I write out the end formula. You'll see it makes sense. Okay, so this is 0. So this is just the F wedge. And now we will, we will use some, just some. So we'll just a little bit manipulate this formula. So we will use the fact that this is effectively, so this is proportional to integral of contraction of times df. And well, the operation of contraction, it's can be written as some plus minus so the operation of contraction of a product of two forms. So the contraction acts by the Leibniz rule. So it acts on the first form plus it acts on the second form. So here I kind of integrate by parts basically. Right? I swap this IV to the other factor. And this guy is 0 just by the dimension. Right? And this is nothing but just a derivative of f along v. But f is a g invariant function. So its derivative along the action of g is 0. Okay. So this is how it goes. So the end result is that this is 0. Okay. So now we actually can simplify this. So basically, we want to work with this expression for the integral of f over the section. But we can further simplify it. So we can write a nice formula that is more explicit. So we will assume that S of m over g is just the vanishing locus of some function. In M. So again, we do this precisely to then go back to the gauge theory situation where G is a gauge fixing condition. So gauge fixing conditions say divergence of the gauge field is 0. Okay, so here we will assume that, so this curve that we're integrating over, it is given by G equals 0. And in that case, we can write that the integral of f with this form of m over g, this can be, first of all, this can be written as wedge some Poincare dual 1 form over M. Right, to a so we have some submanifold d minus 1 dimensional submanifold. Yeah.
Can you explain again why here, how it's equal to 0? What's it signifying? G of equal to 0.
g equal to 0 is just a description of our hypersurface. Assume that this hypersurface is given by g equals 0. I mean, it's a hypersurface, so it should be given by the vanishing of one function, basically, right? Generically, at least. So, so for example, if it's a circle, then x squared plus y squared equals 1. So we just assume that we have this kind of description of this submanifold. Pretty standard. So the point is that this integral can be converted to so we want to write the integral as a delta function of that function of g, okay? So this is the claim, that it can be written like that.
What is the capital B, sorry?
Capital?
Capital B here.
P. This is Poincaré dual 1 form.
Okay.
Dual to S. Dual, so dual to the S of M over G.
Okay.
So this is one, basically that's one of the definitions of Poincaré duality. So the dual form dual to some submanifold in some homology class is effectively a form that looks like a delta function on that submanifold. So here submanifold is a hypersurface of codimension 1, so you wedge with a 1 form. But in principle, this formula is more illuminating. I mean, this is an explicit expression for that. This is just some abstract notion. And nabla Vg is just a derivative of function g, so this is a di dg over dxi. And this is assumed non-zero, right? So this is assumed non-zero. Because g should be a yeah, G should pick the point in orbit. So in itself, it should not be invariant with respect to the group action, right? So more exactly, it should be opposite to being invariant. So we assume that this gradient is nowhere vanishing. So I mean, this is the key end formula that basically works for all cases, including infinite dimensional ones. So basically, that's why we have been driving this. So the point is that an integral over some invariant function can be written as an integral over the slice with this kind of measure. So in particular, this guy in this setting is called the Faddeev-Popov determinant. So this is the gauge fixing condition. And this is the Faddeev-Popov determinant. But in principle, it's just a geometric formula of the setup that I've described. Okay, so let's prove this formula. So this is the answer. But so So we want to get back from this integral over the whole manifold to the integral over the submanifold, right? So what that means, we want to just get rid of the delta function and see that it all works correctly. So we will pick some coordinates. So in the vicinity of our manifold G equals 0, we can pick coordinates G, y1, yn minus 1, right? So G is the normal coordinate, and y1, yn minus 1 along the submanifold, right? So we can write the volume form on M as tilde wedge dg, where this volume tilde involves only, so this is something proportional to dy1, dyn minus 1. So now let's do the integral. So the integral in the right hand side. So the integral of volume form of M, delta function of g of x. So these are all x, what we called x coordinates. dg, so delta function of g, nabla vg, and then we have a function depends on g and y, and we take the integral over g, so this becomes volume tilde nabla vg f of 0y. So this is everything at g equals 0. Okay. So in these coordinates g, y1, etc., yn minus 1, our vector field v has the form that vi dg over dxi, d over dg plus vi dyj over dxi d over dyj. Right? So I just have written out the vector field in these coordinates g, y1, etc., v, yn minus 1. We assumed that originally it was just vi d over dxi, and now we make a change of variables from x, from some abstract coordinates x, to coordinates along the submanifold and the normal coordinate. Why do we do that? Because we want to compare this volume form with the quotient volume form that we had before, right? We're trying to prove that this is equal to this. So let us, so it's easy to see that if you now contract the volume form, so the quotient volume form, which was by definition the contraction of the original volume form with V, at g equals 0, that this is equal to g equals 0, that this is equal to nabla Vg times the tilde. Right, so I now contract the definition of this quotient volume form is the contraction of volume form on M with the vector field V. So I contract it with this, And I use the fact that the volume form on M was this. So the contraction of this part of the vector field removes this differential here and multiplies it by this, which is nothing but nabla Vg, right? And when you contract with that part, it has this dg. The dg here remains, but we are sitting at g equals 0. So, I mean, we're integrating over g equals 0. So that part of the form drops out as well. That just explains this Jacobian, which is nabla Vg, when you pass to the, right? So this is a proof of this formula. So it's easy to see what it is in some examples. For example, if you have a U1 action in the plane, rotation in the plane around the origin. So you want to so you have some rotation in the plane, and we want to pick form the quotient. So the quotient is basically, say, the positive real line. That's the section, the embedding of the quotient into the original space, right? So we want to pass from integrating over the plane to integrating over the positive real line. Okay, this example is maybe a little bit complicated in the sense that, okay, I want to pick the gauge condition, the gauge fixing condition as y equals 0. So g equals y equals 0. This is not a this gauge choice still leaves a Z2 worth of gauge symmetry, right? Because there are some points kind of still equivalent on the real line. But I will not, this will lead to just a factor of 2 in your integral. But we just want to know what is the Jacobian of this. And well, what is the vector field? Well, the vector field is x d over dy minus y d over dx, right? If this is x and y. So V acting on G, or what I call nabla Vg, is just x.
Sorry, in this formula is like delta Vg dot volume tilde. What you wrote in the right hand side.
Sorry.
What you wrote in the right hand side?
Yeah.
No, above.
Nabla Vg times the volume form with the tilde. Here we wrote the volume form on M as the volume tilde times dg, right? So we are saying that the thing that appeared here is the same as IV volume form on M. We're proving this. Because we were proving that this is equal to this. But we start from backwards. We manipulate with this integral. And we arrive here. So what remains to show that this guy is the same as our quotient volume form. To show that, we have to pick suitable coordinates, which are these y, g coordinates, and write our vector field in this coordinate system. And write our original volume form in this coordinate system as well. This is what I do here. And then I just contract this with the vector field, and you see that it's this guy here. So I'm saying if you do it for the plane, you get x. So your integral will be, say, dx dy, delta function of y, x, f of x, y. So this is nothing but the integral over the dx times x f of x y. And you should put a factor of 1/2 here because we're actually not, we haven't fully fixed the gauge choice. We're integrating over the whole line, not over the half line. But I'm saying you get the correct Jacobian. Here what we've done, we've just passed to polar coordinates, effectively. Right? And the Jacobian that you get is can be related to this guy here. But this is a more general formula because instead of integrating over the positive real line, you could be integrating over something like that, some section. And that would give you the correct Jacobian for that. So that's what it does. So yeah, that's the end formula here. And this can be applied to rather straightforwardly now to various other infinite dimensional situations, which is what we will now do. Huh? dx times x, yes. Yeah, which like dr times r when you pass to polar coordinates, right? Right, when you make a change of variables to polar coordinates, you get r dr. And yeah, so the delta should be 0 here, right? Well, x becomes r in polar coordinates. Just that the radial variable, once you sit on the positive real line, the radial variable is just x. Right? Yeah.
Вот пример. Смотри, у нас есть многообразие C. Это M. Ну вот, смотри. C у нас равно M, да? Пусть M это комплексная пусть. Ну, или равно. Пусть наша подгруппа это решеточка. Есть две группы 8. И это все точки тау. Все точки типа M, тау.
Yeah, and I forgot somewhere the group volumes should be somewhere also. I mean, here of course there's not this is times 2 pi, right? Times 2 pi. So there is also a volume of the group standing somewhere. Ah, okay, yeah. So yes, right. So yeah, that's all right. No 2 pi here. So yeah, this is the integral over the quotient. So the original integral is related to this as integral of f volume M should be equal to volume G times this. Volume of the group. I mean full volume, not the volume form. So the integral of a U1 invariant central symmetric function is this guy times 2 pi. 2 pi is the volume of U1. So yeah. At first I wrote that it's proportional to that, but the proportionality constant is the volume of the group. Okay, so here I've just mentioned that actually the original integral is this integral over the quotient or over the section times the volume of the group, right? So where the integral splits into an integral over the fiber, which gives you the volume of the group, times this integral over the section. So of course, this, like I said, this group can be non-compact or can be infinite dimensional even. So then this volume is infinite. So the original integral doesn't make sense. In that case, we just forget that formula and we just kind of take this formula as a definition of our integral, this formula with the delta function. Okay, so first let us rewrite this slightly further. So this formula can now be written as follows. So you can write this as integral d lambda dc bar dc exponent to the I lambda g Okay, so now we've introduced additional variables. So lambda is just integral over a real variable from minus infinity to plus infinity, which gives you the delta function. I mean, I will not keep track of 2 pi or something like that. And c bar c are anti-commuting variables, Grassmann variables. Okay, so this is an integral over the Grassmann variables, which reproduces this determinant. Well, it's not determinant. Well, in this case, it's not a determinant. It's just some function. But if you think about it, if you have a higher dimensional group, right, like you were asking, then you have many gauge fixing conditions, G1, etc., up to dimension of the group, right? And you have also many vector fields generating the action of the group. So instead of this guy, you will have a matrix, right, of derivatives of various functions. And here will be the determinant of that matrix, which is why it's called a determinant. Okay, so the determinant is when you have gauge group of higher dimension. In case of U1, when dimension is 1, the determinant is just this factor. These determinants in general are maybe nicely rewritten in terms of integrals over anti-commuting variables. Because, well, if you remember how they are defined as basically differentiation. So to compute a determinant over this, to compute the integral over this, you have to pick a term which is proportional to c bar c in this expansion, right? So first of all, they are nilpotent, so any higher powers of c are just 0. So the only term you need is c bar c times this, and the integral just removes those c bar c guys, leaving this function here. If you have a determinant, that's even more useful because you'll have something like dc bar a dca, so product over a, exponent to c bar a mab cb. So this is proportional to determinant of m, right? Hope you know that formula, but if not, it's easily proven. So you expand the exponent to the correct power. Then because C's are anti-commuting, you get the kind of epsilon tensor. And that's why you get a determinant. So this can be done in the general case, and that's why it's called the Faddeev-Popov determinant. And these C bar C are called Faddeev-Popov ghosts. Of course, in what Faddeev and Popov were doing, this was an application to gauge theory, so not to finite dimensional integral, but this can be mimicked on a finite dimensional integral like this. And the thing here could be thought of as the ghost action. You know, if you think about a path integral, you usually have an exponent of some action, right, in a path integral. So this is the rudimentary example of ghost action. And it's useful to see, to study the main properties of that action. So what are the main properties of that action? So the main properties, it's an invariance with respect to some transformation, some nilpotent transformation. So let's look at this guy. So this is invariant with respect to the transformation, that is delta xi equals vi of x times c. delta C bar is minus I lambda, delta C equals 0. Right, there are these terms. They are the variations of these terms cancel each other, and this is an nilpotent transformation. Nilpotent means that delta 2, delta 1 of any variable is 0. So you do two variations with two. Yeah, and actually should be also some epsilon somewhere. Some parameter epsilon. Epsilon is a Grassmann parameter. Anti-commuting parameter. But it's a constant parameter, so it's a global symmetry. Well, okay, here doesn't matter because it's a finite dimensional integral, but in field theory this is a global symmetry, so unlike the gauge symmetry that it somehow replaces, it's a global symmetry. So the point is that so in gauge theory this g equals 0 is a gauge fixing. So once you gauge fix, there is no longer gauge invariance, but there is something that remains from this gauge invariance, which is this nilpotent invariance with global symmetry with Grassmann parameter, which is called a BRST symmetry. So this is Iki, Rest or Tutin. So this is BRST symmetry. So this is some global symmetry with the Grassmann parameter. Okay, so how do we generalize this to field theory? So this is and by the way, we've proven before in the first part, we've proven that this integral actually is independent of the choice of G. Right? Remember, we use Stokes theorem and so on. So although there is G here explicitly, but actually it's independent of G.
That goes to 0.
Hmm?
That goes to 0.
What?
That G goes to 0.
No, I mean G equals 0 is your submanifold, your section. So it's independent of the choice of section. You could choose another function, G, that's kind of homotopic to the original one. And there would be no problem. So the value wouldn't change. And the fact the Jacobian, of course, is important for that. So okay. So how does this generalize to field theory? So to see how it generalizes to field theory, it's useful to look at the actual properties of this transformation. So, for example, what is the variation of X? The variation of X is the its variation with respect to the action of your group. So V is the vector field generating the action of the group, right? So your point goes to X plus V times epsilon, right? The infinitesimal shift along the action of the group. The only difference is that now you replace the parameter of the shift by epsilon times C, where C is your ghost. So the point is that this will be the case in all systems. So you take, for example, you have gauge group action, you know how it acts on the fields of your model, you just replace the parameter, gauge parameter, with epsilon times C, where C is the ghost. That's always like that. Then the variations of the ghosts is more complicated because they are new fields of your theory. So we'll see how it works. So for example, how does it work in electrodynamics? So electrodynamics or U1 gauge theory. one gauge theory. So here your Lagrangian is, so the original Lagrangian of U1 gauge theory. So this is gauge invariant, but plus some gauge fixing constraints. For example, in Lorentz gauge we have so this is the gauge fixed action in electrodynamics. What happened here? So this is the analog of your function g, right? This Lorentz gauge, and we're talking about Lorentz gauge. Lorentz gauge. I think it's like that, right? Yeah. And so it's lambda times g, so it's like here, well, maybe some factor of I. And what is this? So you see, how do you write in general the ghost part of the action? Well, the operator in general, there's some operator standing here. What is this operator? This is just the infinitesimal variation of your gauge fixing condition. So this nabla Vg, what is nabla Vg? Is the variation of your gauge fixing condition with respect to the action of the group, right? You act with your vector field on that function. That means that you take an infinitesimal variation in physics language, basically. So, for example, if your gauge fixing is d mu a mu equals 0, and your gauge transformation is delta a mu is d mu epsilon of x, so the variation of d mu a mu is the Lambertian of epsilon of x. And now we just replace your parameter of your transformation with a ghost C. That's how you get this guy. So this is the same as kind of nabla Vg times C. In general, this will be some differential operator, right? Because typical gauges involve gauge fixing conditions involve differential operators. And now this guy is invariant with respect to BRST transformations that have the form delta A mu equals epsilon d mu c. Delta c bar is I lambda epsilon. Delta c is 0. Delta lambda is 0. So this is quite similar to those transformations over there.
And we won't take the lambda g contribution.
And
won't we take the lambda g contribution? I lambda.
Lambda g? Lambda g is this contribution. G is the gauge fixing condition. You don't necessarily have to take Lorentz gauge. You could take some other gauge. It works the same way. So then you compute the variation of your gauge fixing condition, the gauge variation, and you just formally replace your parameter of your transformation by the C ghost, and multiply all that with C bar. That's the recipe how it works. The point is that the Faddeev Popov determinant here is just the determinant of the Lambertian. So you put it back into the exponent using this ghost. Okay. So So anyway, so to this transformation, it's a global transformation. So here epsilon was a function of x. Here epsilon is a constant. Okay. This epsilon is a constant. Maybe I should call it epsilon 0. So epsilon 0 is a constant. So this is a global transformation, and you can compute the corresponding Noether charge. So there is a Noether current. J mu. It's a conserved current. And you can compute the corresponding charge. So charge is the integral of the zeroth component of your current over space in electrodynamics. And again, it will be nilpotent. Because the transformation is nilpotent, so the corresponding charge is also nilpotent as an operator in your Hilbert space of your theory. And then, so the physical states in electrodynamics are in the cohomology of this operator. So physical Hilbert space is the kernel of Q modulo the image of Q. So that's one way of describing physical Hilbert space in electrodynamics. And this is the general procedure. So the states in the image of Q are necessarily of zero norm, right? Because Q chi squared is chi Q squared chi. Because it's nilpotent, this is zero.
In our string, we like this image Q is related to some H spur.
Yeah, that's right. Yeah. Mm-hmm. Yeah. Exactly. So now we will apply all this stuff to the string model, and there, indeed, you can either compute the cohomology of Q, or you can get back to this description without Q that we had last time, with the spurious space, physical space, and so on. Yeah. So this will be just a more condensed way of describing that. Okay, so this is just a reminder about electrodynamics, because, well, this Faddeev-Popov method or BRST method and so on that arose in non-abelian gauge theory. So in electrodynamics, it's a bit less necessary, maybe, but it could be used depending on the taste. But in gauge theory, it's really necessary because in non-abelian gauge theory, because in that case, the ghosts are not free. They interact with the Young-Mills field. So that's why they were necessary in the work of Faddeev, Popov, and so on. So here they are free. So they are just some.
In non-abelian thing, you have also indices of lambda, right?
Yeah, sure. You have the indices of lambda, and also the ghosts, they live in the Lie algebra of your gauge group, so they will also have indices. And you will have some covariant derivative here, which is why it interacts with the Young-Mills field. So there it's they're really essential. So actually, in our string application, our string applications will be perhaps somewhat closer to electrodynamics, in the sense that the ghosts will also be free. But still, it's interesting enough. So BRST symmetry in the string model. So first of all, so our gauge group in this case is the group of diffeomorphisms times the Weyl transformations. So we have morphisms of world sheet times Weyl transformations. based on this parallel with what we just discussed, so what are the original fields of our model? So the original fields of our model are the metric and the x fields. So bless you. So the variation of the metric is epsilon times is this. So as we already discussed in the case of non-abelian theory, the ghost will generally live in the Lie algebra of your gauge group. So here the Lie algebra is the Lie algebra of vector fields. So the Lie algebra of diffeomorphisms is the Lie algebra of vector fields. So so we will introduce the ghost. That's a vector field on our manifold.
They will live in ghost will live in Lie superalgebra.
Hmm?
I think they will live in Lie superalgebra.
Well, it's a Lie algebra of diffeomorphisms with inverted parity, so to speak. So yeah, formally you could think of it as a superalgebra. Yes, that's right. So. So you should think of the ghost as being a vector field on your a Grassmann odd vector field on your worldsheet. Well, here I've lowered the indices, but that I can do, of course, using the metric. And this variation, there's also a ghost for Weil symmetry. So this is just a variation of your metric with respect to Weil symmetry, right? The variation is just the metric times some function. And we replace this function by another ghost.
So if I explain what is CY.
It's a ghost for Weil symmetry. So the Weil, the gauge group is not just diffeomorphisms, but also Weil rescalings.
For the rotation part.
No, it's not the rotation. It's is the rescaling gamma alpha beta to e to the omega gamma alpha beta, something like that. Where omega, this is a function of sigmas. Rescaling by function, right? We discussed that the Polyakov action is invariant with respect to rescalings of the metric by function. So, and we use that to bring the metric to a flat form. That means that once we pick some gauge fixing condition, so the gauge fixing condition we want to pick is that the metric is proportional to the unit metric, actually is equal to the unit metric. So we use diffeomorphisms first to bring it to diagonal form, proportional to the unit metric, and then we use Weil transformations to set it equal to the unit metric. Then we have to take a variation of that gauge fixing condition to compute the Faddeev-Popov determinant, right? In particular, this involves variation with respect to Weil rescaling. So there is a Weil ghost. Okay, and the variation of the axis is just the action of vector fields on axis. It's like that. So these transformations, they describe the BRST transformations of the original fields of the model. So this is like the variation of delta x I equals vi epsilon that we just discussed, or the variation of delta a mu, which is d mu c times epsilon. Okay, so in electrodynamics, the original field was a mu. In the finite dimensional integral, the original field was x coordinate. So these are the analogs of those transformations for this model. Then we also have to write out the transformations of c bar c, and I mean here there's c bar c and lambda, and so on, whatever other fields we've introduced. So far, just this piece. So the gauge fixed part of the action is written as the Polyakov action. So this is, again, in electrodynamics, this would be minus 1/4 f mu squared. So this is the just as a parallel. So plus I. Now we will write the ghost part of the action. So the ghost part of the action is so what has happened here? So first of all, I've introduced the gauge fixing condition, which says that gamma alpha beta equals gamma alpha beta 0. So gamma alpha beta 0 is a fixed reference metric, which ultimately we will think of as being the identity, or the Minkowski metric, let's say. So B alpha beta is just a Lagrange multiplier for that condition. It's the analog of lambda, okay? Just in this setup, it's called B. So this is kind of like lambda. And this is the ghost part. This is the variation of the gauge fixing condition with respect to the gauge transformation. So just this guy. So this is reference metric. So later on we will have gamma alpha beta 0 equals eta alpha beta. But it could be any other metric that we like.
B alpha beta is here symmetric.
It's symmetric, yes.
Here, so you have expressed SGF in form of sigma model. In form of sigma model, you have expressed.
Sigma model?
Yes.
Well, yeah. I mean, the sigma model is just this Polyakov action is a sigma model with flat target space. By definition, basically. I'm saying this is the ghost action for this string model that we were studying, right? So once we fix the gauge to conformal gauge, so that means if you think about it as generalized conformal gauge, that just means that you fix the metric to any arbitrary metric you like. That could be just eta alpha beta, for example. And then it has a ghost contribution. Just like before, we need to compute the gauge, the variation of the gauge fixing condition. So this is like, again, in earlier language, this is like nabla Vg, okay? This is like g equals 0. This is nabla Vg, the variation of your gauge fixing condition under infinitesimal gauge transformation. And this guy, b small b, is the anti-ghost, so like the analog of C bar. Just for whatever reason, here it's called B. It's also symmetric. But this is an anti-commuting guy. So this is a bosonic variable. This is kind of fermionic variable, or anti-commuting. So B alpha beta C alpha Grassmann. Variables. And so the BRST variations of these guys are similar to what we had before. So we had the variation of C bar is lambda. So this is the analog of that. This is kind of C bar. This is lambda. and the variation of lambda was 0, so here we also have variation of capital B is 0. Well, and we want our, we expect this to be a nilpotent transformation. So first of all, let's look at this while ghost. So the while ghost just tells you that it just enters linearly as Lagrange multiplier. So it just tells you that B is traceless. So B is not only symmetric but also traceless. And that's the only role C while plays, just to tell you that this is traceless. But the more, slightly more complicated part is the variation of the C ghost. So in the previous examples we had that the variation of C was 0. But that is because the gauge group was abelian. So here, so if you remember Yang-Mills theory, so in Yang-Mills theory, like you said, C should carry an extra index, right? So delta CA is proportional to F ABD CB CD times epsilon. So it's proportional to the structure constants. So here, here since we have a group of diffeomorphisms, it's a non-abelian group. Two vector fields do not commute in general. So we expect that the variation of C will be something quadratic in C involving the structure constants. But we can derive that using nilpotency. So we want to we want BRST to be nilpotent. I mean, there are various ways of deriving it. You can derive it from first principles and so on, but this is just like a quick way of deriving the C transformation. So you see the transformation of X is this. So now if we do a second transformation, so we will need the transformation of C. So that's where we can get, from where we can get it. So what we will require that, so delta epsilon 2, delta epsilon 1 of X be 0. So let's compute this. So delta epsilon 2, delta epsilon 1 of X mu is, so the first transformation we know is this one. So this is C alpha d alpha X mu. But now we do the second transformation. So this is epsilon delta epsilon 2 C alpha times d alpha X mu plus epsilon C alpha d alpha delta epsilon 2 of X mu. And this, of course, we also know. This is just epsilon 2 C beta d beta X mu. So now we write this. So this is epsilon 1. Sorry, this is epsilon 1. So we get that this is epsilon 1 d epsilon 2 C alpha d alpha X mu plus epsilon 1 C alpha epsilon 2, and then there are two terms, right, where the derivative acts on d alpha C beta times d beta X mu plus C beta d alpha d beta X mu. Right, I just act with the derivative. But you see, the second term doesn't contribute, so this goes to 0, because this is symmetric in alpha and beta, and it's contracted with the C alpha C beta, which is anti-symmetric with alpha and beta. Right? So we're just left with these two terms. And we just need to find the coefficient in front of d alpha x mu, basically. So what we get is this is epsilon 1 delta epsilon 2 C alpha plus, so minus epsilon 2 C beta d beta C alpha times d alpha x mu. I've swapped the alpha and beta summation here. I've changed alpha and beta. So then you get this. Minus is because you commute epsilon 2 with this guy. And so if you want this to be 0, then this bracket has to be 0. And this gives you the transformation of C. So, so this should be 0. So this gives you that delta C alpha is epsilon C beta d beta C alpha. And you see this, since C is a vector field, so the variation of every, like as we discussed, the variation of all variables looks like BRST variation, looks like the action of the gauge group on this variable. So if C is a vector field, it's acted upon by diffeomorphisms via commutator with the vector field, right? But then we replace the parameter, the gauge parameter, with C. We have to replace parameter with C. So this is like the vector C vector field acting on itself. That's what it means, like diffeomorphism generated by C acting on itself. So so that's it. And
Delta beta C alpha is something like commutator.
yeah, this is an anti-commutator, yes. Anti-commutator, yes. That's what you were asking about, the superalgebra, yes. So you replace commutator by anti-commutator. That's basically it. So, okay, so yeah, next time we'll discuss the energy momentum tensor of the ghosts and how the Weil anomaly, how it leads to central charge being 0 with a once you include the ghosts. So that's it. And our next lecture will be in 2 weeks from now. So not next time, but in 2 weeks from now, because we have this conference next week. So yeah, see you in 2 weeks.